Welcome back. Okay, so in this lecture, I want us to start computing slightly more advanced probabilities, things that might be a little unintuitive, things that might involve some pretty big numbers. And I'm going to illustrate some of these concepts on the birthday problem. So I'm going to state this problem really quickly. You've probably heard of it before. So if there are n people in a room, if there are n people in a room, how large does n have to be before there is at least a 50% chance that two people share a birthday? There are n people in a room. How large does n need to be for at least, I'm trying to state this kind of precisely, at least 50% chance of at least two people sharing a birthday. A 50% chance of at least two people sharing a birthday. Now, you've probably seen this before. If you have young kids or nieces or nephews, maybe you can ask them this problem. And the off-the-cuff kind of intuitive answer that people usually give is something like 365 divided by 2. That's just kind of the off-the-cuff answer a lot of people give. And that's actually really far from the true answer. So this is kind of an unintuitive probability problem. And it's also pretty hard to compute using the naive way of adding up the ways things can happen. So I'm going to show you another trick that is going to be useful everywhere, which is it's actually much easier to compute the probability that nobody shares a birthday, and then take 1 minus that probability. The probability that at least two people share a birthday is 1 minus the probability that no people share a birthday. So that's going to be a really, really important kind of trick to make our counting these possibilities easier. And we're also going to illustrate that this is just kind of unintuitive and hard to count the naive way. Okay, so let's get into it. I'm going to draw a picture. So I'm going to illustrate my n people as kind of just standing in a circle, dot, dot, dot. Okay, this is just like a cartoon of n people standing in a circle in a room trying to compare birthdays. And so the first thing I want to do here is just count how many comparisons are there. So let's say that this is person 1, person 2, person 3, 4, dot, dot, dot. And what I'm really trying to do is I'm going around the room looking at unique birthday comparisons. So if two people share a birthday, it could be person 1 and 2, person 1 and 3, 1 and 4, dot, dot, dot. It could be person 2 and 3, 2 and 4, 3 and 4, and so on and so forth. So one way to do this would be to literally have everybody kind of pair off in every unique combination and just compare their birthdays. And if you calculate this number, so there's n people in a room, let's say this is person n, then the number of comparisons, person 1 compares with n minus 1 people, person 2 compares with n minus 2 people, because they've already compared with person 1. Person 1 compares n minus 1 to n minus 2, person 3 compares with n minus 3, and so on and so forth, dot, 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 until the last person has already compared with everybody, so they don't need to compare with anyone else. So all of these integers, plus 2, plus 1, plus 0. And this is actually an easy formula to compute. There's an old story that Gauss computed this when he was 3. His parents were maybe getting fed up with him, so his dad sent him off to a corner, add up all of the numbers from 1 to 100. He thought this would keep Gauss busy for a couple of hours. Gauss came back moments later with the formula, which is n times n minus 1 divided by 2. Okay, good. That's how many comparisons, unique comparisons, you would have to do to just brute force check all-to-all comparisons. And this gives you some intuition for why this number is much, much smaller than 365 divided by 2. So this number actually gets big faster. So if n is about 20, so for n equals 20, this number of comparisons is, I don't know, 20 divided by 2 is 10, times 19 is 190. That's already bigger than 365 divided by 2. So, you know, we're looking for a 50% chance of 2 people sharing a birthday. So you can imagine with order of magnitude, rough order of 20 people, you should have enough comparisons to get close to 365 divided by 2. A 50% chance of some of these comparisons resulting in the same birthday, okay? This is very heuristic. This is not how you compute the probability. There are a lot of things that can go wrong because each of these unique comparisons, if I do all of these 190 unique comparisons for 20 people, I might end up double or triple or even quadruple counting. Because notice that this says that it's the probability for at least 2 people sharing a birthday. So there could be 3 people in this room that share a birthday, or 4 people that share a birthday, or 5. And so I could be double counting a lot in this number. So the answer is not n equals 20 or 19. We have to precisely compute the probability of at least 2 people sharing the birthday. Okay, good. Now, the way you actually do this, the easy way of doing this, and maybe I'll just do this in red over here, I'll kind of start the problem, is you say that the probability that I'm going to use shorthand. Oftentimes, the thing inside my probability is shorthand. So it's the probability of an event. So the probability that at least 2 people, greater than or equal to 2 people, share a birthday. This is equal to 1 minus the probability that nobody shares a birthday. Okay, so if 2 people share a birthday, 3 people share a birthday, 4 people, 5 people, 6 people, so on, that's a set of events that add up to this. The complement of that set, if 2 people don't share a birthday, 3 people don't, 4 people don't, et cetera, the complement of that set of events, of things that could happen, is that no people share a birthday. And so probability that nobody shares a birthday plus the probability that at least 2 people share a birthday has to add up to 1. Okay, this is like the law of total probability, essentially. And it turns out that this is much easier to compute. Much easier to compute than this. Okay, so in a minute, I'm going to show you how to compute the probability that no one shares a birthday. That's really easy. Just roughly sketching through the probability that 2 people or 3 people or 4 people share a birthday, this one's challenging. This one is hard to compute. And I'll just roughly show you what this means. So the probability that greater than or equal to 2 people share a probability is, equal to the probability that, so the probability that greater than or equal to 2 share is equal to the probability that exactly 2 people share, the probability that exactly 2, plus the probability that exactly 3, plus ... Okay? And it's even worse than this, because I could have, what if these 2 people shared their birthday, and then these 3 people shared their birthday, and then these 5 people shared their birthday? So I'd essentially have to, there is a way of writing this out, and it's a mess, and I'm trying to keep these videos kind of short. So maybe as a homework exercise, try to actually enumerate all of the possible ways that this can actually happen, that you can get exactly equal to 2, exactly equal to 3, exactly equal to 4, and then see, am I missing anything? Are there other terms in here, plus other terms? Try to enumerate how many ways there are to get greater than or equal to 2 people sharing a birthday. And I think very quickly you'll realize that you're going to get these nested, horrific sums of cases. Like, first thing I'm going to do is I'm going to say, okay, person 1's birthday, we're just going to say that that's a number, that's a date. So then I'm going to go and calculate what's the probability that person 2 has the same birthday, okay? Then I'm going to say what's the probability that person 3 has the same birthday as either of them and that, given that probability of 1 and 2 was not the same birthday. So you're going to get all of these like mixed if-then statements to try to count these probabilities. This is a mess, okay? That's kind of a self-guided study problem, is try to actually write down all of these combinations. It's going to be a mess. It's going to take you a long time, very hard to compute. Let's do it this way. The probability that no one shares a birthday, that's actually much, much easier. So the probability that no one shares, and this is kind of like those, that poker hand example. So what we're going to do is we're going to essentially say that the first person's birthday can be anything, okay? Because it doesn't matter what the first person's birthday is. Once we've determined the first person's birthday, let's say it's June 17th, now we know that the second person can not have the same birthday as the first person, okay? So I'm going to draw a little picture here. I have like the first person's birthday, the second person, the third person, ... all the way up to the nth person. And this person can choose from any one of 365 days, and it doesn't matter. Okay, so this is person 1. Now, person 2, out of all of the 365 days that they could have, 364 of those days mean that they will not share a birthday with person 1. So there's 364 out of 365 possible probability that person 2 will not share a birthday with person 1. Now person 3, these first 2 birthdays are already chosen. This one was June 17. Let's say this one is October 3rd. So now the third person, out of all 365 days of the year, this person has 363 possible days that they can choose from. So if you randomly assign person 3 a birthday, 363 of those choices out of 365 will not cause them to have an overlap with person 1 or person 2. And you can keep going and going. We have 362 left out of 365, 361 left out of 365, ... Finally, 365 minus n plus 1 over 365. And I can fill in here for person 1, out of all of the 365 days of the year, all 365 of those days don't cause person 1 a conflict because they're the first person. They're not being compared. Person 2 compares with person 1, person 3 compares with person 1 and 2, and so on and so forth. Person 1 can pick all of those 365 days. So the probability that no one shares is essentially this product here. This is the probability that no one shares a birthday out of n people. And you could make this a little more formal. You could say, well, this is the number of ways that you can have unique birthdays, number of unique birthdays, divided by the total number of choices possible. Now, the total number of choices is obviously just 365 to the n. All of these n people could have any birthday. The total number of birthdays is 365 to the power n. That's the total number we're dividing by. The number of unique birthdays where no one shares a birthday is this product here. It's, maybe I'll write this in orange. This number of unique birthdays is 365 factorial divided by 365 minus n factorial. And remember, this is that number that we had that was if you have sampling without replacement, right? So everyone's sampling a birthday, but for them to be unique, when someone picks June 17th, all of these have to sample from the remaining 364. And if this person picks October 3rd, the remaining people have to sample from the remaining 363. The pool gets smaller for us to have unique birthdays. So these are essentially the numbers I'm dividing by. So my formula is really simple. Probability no one shares a birthday is 365 factorial divided by 365 minus n factorial times 365 to the power n. Okay? And this is something that's computable. This is very, very hard to compute. This is very, very easy to compute. Okay, and so this is actually going to be a homework problem for you, is I want you to actually code this up for n equals 1, 2, 3, write a for loop for, n equals 1 until some condition is met. And you're actually going to compute this object here, and you're going to compute the probability as n increases. And what you're going to find is that very quickly, for about, in fact, for exactly n equals 23, at n equals 23, the probability that no one shares a birthday drops below 50%. And so the probability that at least two people share a birthday goes above 50%. So for n equals 23, this number drops below 50%, below 0.5, meaning this number goes above 0.5. So this is the exact number. And you're going to write a for loop to compute this number for all of those n. You're going to plot that probability, and this probability, and you're going to find that n equals 23 is where this crosses the 50% line. And so if you were going to turn in a homework assignment, I might ask you, what is the probability? What's the exact probability when n equals 20? Clearly, it's going to be a little bit less than 50%. Not a ton less, but a little bit less. Okay. Now you can try this on your calculator. So I didn't, I'm not coding this up right now. That's a homework problem for you. But I can go and try to do this on my calculator. And what you're going to find actually is that this number, you can't type this into your calculator. You can't type in 365 factorial divided by, because immediately you're going to get an error, because this number is way, way, way too large. This number is bigger than your calculator can easily represent in all of its, bits of representation. So you can't actually write this down in your calculator. Now you could try to go to Google and type this in. Let's do that. Okay, Google says it's an undefined number. Google's apparently not as smart as I thought it was. You can go to Wolfram Alpha, and you can type this in. So if you actually type this into Wolfram Alpha, you actually get a number. Let me just type this in. Okay, so the probability for 20 days is about 0.589. So n equals 20 gives a probability of no shared of about 0.589, which means that the probability that two people share a birthday in a room full of 20 is about 40%, 41%. So actually pretty good odds, but not 50. So you can compute this in Wolfram Alpha. You can write a for loop. If you were going to write a for loop, you can't just type this in easily and say go, because it might error out. If it tries to compute this number first, it's too big, it's going to error out. So what I would actually do is in my for loop, I would actually multiply by the next number in the sequence. This is the formula you actually want to use when you're computing it. I'd say for, k equals 1 to n, this is my first probability. Then for n equals 2, I multiply it by this one. This is a tractable number. It's close to 1. Then for n equals 3, I multiply it by this number. This is a reasonable number. It's close to 1. And so as you multiply up, all of these numbers are reasonable, and it's much easier to compute than trying to compute it from this formula directly. Okay, so that's the homework problem. Write a for loop, check these different probabilities, make some plots. But it gives a couple of important ideas here. Probabilities are sometimes unintuitive. So the way you actually count things, it might be really hard to compute the thing you actually want. Actually counting the probability of greater than 2 people sharing a birthday is very hard. There's all of these weird edge cases. Maybe 3 people share a birthday, maybe 4 people, maybe 2 people share a birthday and another 2 people share a birthday. There's all kinds of weird stuff that can happen, very hard to compute. Very often in those cases where it's hard to compute something, it's easy to compute the complement of that thing not happening. And so that's what we did here. It's a very simple formula to compute the probability of no shared birthdays, which allows us to get this really nice, easy expression. Parting thoughts. You should always be asking yourself, what assumptions did I make? So obviously, we are assuming that there's no leap years. We're assuming that there's exactly 365 days. No one can have a birthday on February 29th. If you in the audience have one, I'm sorry. Please write something in the comments so we can see how many of you there are. We're also assuming that all days are equal, which is clearly not true. Some seasons people have more babies than other seasons. So take your birthday and subtract 9 months. If you're a mid-November baby, maybe you have a Valentine's Day conception. And there are all of these different kind of biases in these probabilities. Like all 365 days are not equal. So there will be these kind of hot spots where it's more likely for people to share a birthday than others. And I want you to think about, how would these calculations change? What data would I need to make a more refined estimate? If I was in a room with 23 people and 5 people had the same birthday, would I think that this was a random sample? Would I think that that's normal? What are the chances of that, given these assumptions that I made? Okay, code it up, try it yourself. It's kind of a fun problem to test your intuition. Thank you.